Howdy and welcome back. So let's go ahead and get into our introduction to trees. But before we do, let's reminisce on our old friend linked list. Do y'all remember this? So this is a doubly linked list here. We also talked about singly linked list, and the MP actually had you implement a doubly linked list. In lesson, we went over the singly linked list variation. This is a linear data structure. If we look here, data is kind of arranged sequentially. One data comes after the next, one datum comes after the next, etc. And we just move from it, from one to the next, until we arrive at the end. And the question is, okay, well, can we extend this idea to create another type of data structure whose underlying structure is not simply this linear sequence of nodes, but one that is non-linear, hierarchical in nature, and perhaps tree-like in appearance? And the answer, given the topic of today's lesson, is obviously yes, we can do that, and we will. So I want you to just look at this and think about, how does the traversal actually work? In the case of the singly linked list, we have an entry point, right? We call this the head. And then from that, we can move to the next node within the sequence. How do we do that? Well, we follow a pointer, right? We go from, say, the head, that node, you look at the next pointer, and we move into the subsequent node. And we can continue this operation until we observe a node whose next pointer is the null pointer. So notice how this operation is going. What if I told you, okay, instead of having some sort of head, let's say we have some sort of root. And let's say that instead of moving to the next node, you can either move to a node that resides to the left of this node called root, or you could move to a node that falls to its right. Now, if you think about this, how do you determine if we visit this node? It's not like, our linked list where we're guaranteed to go just to the next, to the next, to the next, to the end. And this kind of idea, there's some decision making. We're at this particular node and we go, well, do we want to move left or do we want to move right? And how could we use kind of this tree representation? In this case, it's kind of an upside down tree representation. If you can see, like, here's kind of the trunk, and here's kind of maybe one branch, and here's another branch, and you can think about this, branching out further, and then we really get kind of this tree-like structure, and that's where the names kind of derive from. But just thinking about this, how, would we work on, say, a traversal of this? How would we interact with this data structure? Well, I guess I answered the question a bit prematurely. In this slide, we say, sure, we can create a tree. And the slide's title is Onward to Trees. So we can create binary trees. This is going to be a tree where essentially each node is going to have pointers to two child nodes, which we'll talk about. But there will also be trees whose node can have an arbitrary number of children. And we'll get into this terminology in the next few slides here. But just kind of look at this, take it in. Just like our linked list, we store data in nodes. This is no different. And we have pointers to other nodes. Again, no different than what you've seen before. It's just the connectivity here that's slightly different. And obviously, because we are dealing with this structure that is not linear, to move from one node to the next node, we have to determine, well, are we going left or right at this particular branch, if you will. So we'll get into that here shortly. But we can see here that just like the linked list, a linked data structure can emerge through these pointers to other nodes. And with proper consideration, we can go ahead and formulate a structure that resembles, in this case, an upside down tree. So let's get into some of the terminology first here. What I'm considering a node is this. So how we've represented a node in our programs, up until this point was as a struct with some sort of data and some pointers to other node objects, which in itself kind of presents an idea of recursion. If we look at this, these connections we can think about as edges. They're connecting, say, one node to another in some sort of sequence. So some terminology. We have a parent node. right? And the parent node can have children nodes. So in our case over here, we could say the root is a parent node and it has two children, the node storing the elements or the characters G and T. These are the node storing A's parents, or excuse me, children. So let me go ahead and highlight this. Here's the parent. It's this person up here, the root in this example, the children right over here. It's who the root is pointing to, the next nodes within this nonlinear sequence, if you will. So again, that's just some terminology. We have this parent node idea, and then we have children nodes. And just likewise, and which I didn't actually show in this initial diagram up here, is that each child node is going to have one parent. And how we're ultimately going to set this up is that a node is going to have some data as well as a couple of pointers, a pointer to its left child, to its right child, as well as a pointer to its parent. And we'll get into that here shortly. But again, just look at the terminology here. This is what we're focused on. We have this idea of a parent node that has children, one or more children. We have this idea that the child node is going to have one parent. And moreover, we can start, taking this, I guess, analogy to a family and take it out or branch it out a bit more and go, nodes with the same parent are going to be called siblings. So if we look up here, we can see a lightly colored red node that has two children, both colored in blue. We can say that these two blue children are siblings because they're derived from the same parent. Now we could continue this on, and what we'll see here is that each tree essentially has subtrees who are trees in and of themselves. So if we look at this and begin going, okay, well, let's look at this node here, this one blue one here. We can see that it has two children, these lightly colored green nodes. And those two green nodes, because they arise from the same parent, are known as siblings. Now, just some additional information, we alluded to this a bit earlier, but the top node in a tree is going to be called the tree's root node. Just like the head in our linked list kind of provided our entry point into that sequence of dynamically allocated objects, the root is going to be our entry point into our tree. So it will be kind of the first node. It will be, I guess, I don't know if you want to call it the trunk of the tree, but it's down there, kind of what's connected into ground. And again, view this as an inverted tree, right? We can see here from the root, branches are slowly emerging through these edges, and that granularity of the branches kind of increases as we begin expanding out. Some additional terminology, we have not kind of mentioned this yet, but nodes that do not have any children are going to be called leaves. So we can see here that this node off of the root has no children, so it is a leaf. Likewise, this node off of one of the parent's children likewise has no children, so it would be considered a leaf. Likewise for this node down here. These are all nodes though, so like the root is a node. The root's children are nodes. The leaves are nodes. All we're doing is providing some sort of classification on those. We're giving names to some different types of nodes, if you will. For instance, the entry point into our tree, the root node. So that would be a node named root. These leaf nodes are simply used to characterize a classification of nodes. So nodes who have no children. Likewise, we have the idea of a parent node, which you could say, okay, it's going to have some sort of children. A child is going to have a parent node, unless it's the root. But the key takeaway here is that these are all nodes. We're just giving different names to different presentations, or I guess nodes who have certain shared attributes kind of amongst them. Like leaves have no children, so you'd expect their left and right pointers, and we'll get into this soon, would point to the null pointer. So we could say that because, say, leaf 1, leaf 2, leaf 3 all share those kind of that same configuration, we're going to go ahead and just assign the name and characterize them as leaves to aid our discussion here. So Hopefully that makes sense. Again, they're all nodes. We're just characterizing them based on their presentation or attributes. So that looks like a duplicate slide. Probably wanted to do something with that and then failed to do so. But anyways, let's continue on. I know what's in this slide set's precisely what I'd like to cover. So now let's talk about kind of two different ways. Let's just introduce the terminology. So the depth of a node is going to be the number of edges from the node to the tree's root. We're going to say this is kind of top down, okay? So if we go ahead and we can see here, the integer values stored within these nodes are going to be communicating that particular node's depth. So again, it's from the node to the tree's root. So we can see here that there's one, if we call this node A, let's go ahead and put some names to these nodes. Give me one sec. So if we go ahead and look at this, say from node A to the root, we have one edge. So its depth from the root is going to be 1. And that's denoted here. Likewise to B, we see a single edge there. So its depth is going to be 1 as well. C's depth from the root node is going to be 1. So let me just go ahead and, I guess I'll do a different color. 1, 2. It's 2 edges away from the root. So we can see here that node C's depth is going to be effectively communicated as 2. Now let's go ahead and look at node D over here. It's going to follow suit. It's at the same depth as node C. So we'd expect its depth to be 2 as well. Look, there's one edge to get from D to B, another edge to get from B to the root. There's 2 edges separating D from the root. Therefore, its depth is going to be 2. Now, E's kind of down there at a different level from the others. It's going to be 1 edge, 2 edge, 3 edges from the root. So it will have a depth of 3. If we go ahead and look at this, we can see that to get to the root, the path that we follow here would be from E to D, D to B, B to root. And to get across those hops, we'll traverse 1, 2, 3 edges. So E is at a depth of 3. Now height can be a little confusing because we looked at depth and I said it's top down. So it's kind of like going from the root. So the root would be effectively a depth of 0. One kind of hop from the root would be a depth of 1. So notice it's increasing as we're going from the root down to the leaves. Height is going to go the other way. So the height of a node is going to be the number of edges in the longest path. This is key. Do not neglect this feature here. It is the longest path from the node to a leaf. So if we go ahead, and again, you can think about this as ground up. So starting from, assuming this is the ground here, how far away from we are it. So all leaves are going to be 0. They're at the ground level. And, I could have, I guess, drew that up to accommodate the leaves a little better, but they're all, again, this is the distance from a node to a leaf. A leaf is a leaf. So it's going to have a height of 0. If we look at, say, here, let me go ahead and quickly number these or label these so we have some discussion points. We can see here that E, C, and A are all leaves. They have no children. So their distance from that node A to a leaf is 0 because it is a leaf. Now, if we want to look at, say, a node like D, it is not a leaf. So we have to find its longest path to a leaf. We can see that D has no left child. So we'll go ahead and go right. And lo and behold, if we take one move, we've arrived at a leaf. So the height of node D is going to be 1. And notice how this is like, again, from the ground up, assuming that green kind of squiggly thing down there is grass. Now let's go ahead and look at node B here, and we see 2. Okay, again, this is the longest path from a node to a leaf. So we have 2 options, left and right. There's a child in both directions. So let's go ahead and go left first. We can see that moving from B to C, moves us from a node to a leaf. In this case, we've effectively traversed one edge to do so. So in this case, we've observed a path length of 1. But remember, we're looking for the longest path here. So if we go the other direction, we move from B to D. That's going to be essentially 1. And if we can, and we arrive at D and we notice we're not at a leaf yet. So we need to keep going. We can't go left on D because D has no left child. So we're going to go ahead and go right. In this case, and if we preserve the height of D within D, we wouldn't have to continue this traversal. We could just ask D, hey, what's your height? And some trees will store this information. But anyways, we'll go ahead and continue the traversal. And guess what? From B to D to E, we've arrived at a leaf traversing 2 edges. So the height of B in this case will be 2 because that is the longest path length from that node B to a leaf. And again, we've said here the height of a leaf is 0, and the height of the tree is going to be the number of edges in the longest path from the root to a leaf. Now, if we go ahead and begin to calculate this for our tree, we'll begin at the root node, and we can see here that to the left of root, we have a leaf. So that's going to be effectively a distance of 1. Now, I'm not going to go through the whole motion here. I'm just going to assume that the height is stored within each node. So let's assume that B is already getting calculated. So we'll step right of the root, arrive at B. We'll ask B what its height is. B will say 2. Well, guess what? That means we've traversed one edge to get to B. B is communicating a height of 2. 1 plus 2 is going to give us a height of 3, which is going to be the longest path from the root to a leaf. And that path is going to be this one, which requires us to traverse 1, 2, 3 edges. So the height of our tree is effectively 3. Okay, so moving on, a little bit different discussion here is going to be this idea of a subtree. So a subtree is a tree wholly contained within another. So in our diagram, the green nodes comprise the right subtree to the red node. So if this is our root up here, we can say that our root is going to have both a right, and this is assuming a binary tree in that we only have left and right as options here. So there's only going to be at most 2 children. So if we go ahead and look right, we have the right subtree, which is all of the nodes there. If we look left, the blue node would comprise the left subtree. So here's our left subtree. And over here is our right subtree. So again, just some terminology, understand that a subtree is a tree wholly contained within another. I mean, you could think about it. If we have this pointer to the root, we could have another root pointer. You could literally call it another underscore root pointer to say the root of the green subtree or the root of the blue subtree then. And then we could view it as a tree because the same kind of rules apply, because this idea of a tree is kind of recursive, right? If you start thinking about it, it's built up. It's kind of like a tree within a tree within a tree, if you've seen Inception. Hopefully you all see where I'm going with that. But just, I guess, try to go ahead and affirm this here is, so we have this whole tree structure. I'm just going to focus on the tree that would result if we considered, say, this as a root. We can see that all the green nodes would be encompassed within the tree, assuming derived from the root's right subtree. So does that kind of make sense, hopefully? At this point in class, I'd probably be going like that to gauge the response. So we're going to move on to binary trees. So I do hope this introduction to trees has proved somewhat informative, that some of the vocabulary is a bit clear. I will go ahead and acknowledge that at this point in the class, we're getting into material that I haven't taught in a 100-level course before. So, and that's the teaching, it's not a problem. It's, I'm not as familiar with where, y'all might require more attention or clarification. So if, particular areas in these discussions come up as, maybe not as clear or intuitive the first time you see it, do make a post to the forum so that I'm able to go ahead and clarify whatever it may be, as well as write down kind of in my notes that, this needs more focus the next time around. The stuff up to this point, I've gone through, multiple iterations, so I have a pretty good idea. But if y'all could help me with that, that'd be awesome. But again, this will be a really fun topic, and I hope you all find it as enjoyable as I do, and hopefully it's as clear as I think it is in my presentation. So let's go ahead and move on to binary trees, which we've talked a little bit about right now. And we're going to just introduce the topic very generally. We'll do the same with the unbounded branches, same with the other tree representations, and then we'll actually spend a bit of time on the binary search trees and continue to carry that on through the week.